We can FERC. So I present a fair representation in machine learning. So the first question is why fairness? Machine learning system are trained using biases data that could contain racist, sexist, or discriminating data. And such biases can be learned and even amplified by the AI system. And such system will therefore predict unfair outcomes and even be discriminating towards some individuals. So one method to provide fairness-aware prediction is to develop techniques that remove biases that could lead to unfair predictions in data, and we call this technique learning of the fair representation. So this fair representation is transferable. That means it can be used after to train a prediction model, and we assume that using the new representation that is supposed fair, the machine learning model is most likely to produce a fair outcome. So what is a fair representation? We have the input data x and sensitive attribute a. So we want to learn the new representation z, where z will satisfy some fairness constraints, such as the statistical parity, equity of opportunity, or equalized odds, or individual fairness. And z must maintain information in x as much as possible. So many techniques have been proposed in the literature to resolve this issue. The first technique is learning fair representation, which is like the baseline. The first model proposed for fair representation learning, and this model is basically use optimizations to produce the fair representation Z. And other models based on variational autoencoders extend the variational framework to integrate some adaptations to remove dependencies on sensitive variables in the latent space, and other method based on adversarial learning try to adapt the first method layer fair representation to remove sensitive attributes by adversarial learning. So the first method is to learn fair representation. Here they define three main objectives that should be satisfied by the latent space Z. So first, the latent space Z should retain as much information as possible in training data, and this is reconstructability. Another constraint is that it should satisfy the statistical parity. So this depends that the information should be written from X except information about sensitive attributes. And also the representation Z should maximize the prediction of output Y. So based on this basic definition, they define a loss functions with different hyperparameters. So the first loss Lx is the reconstruction cost that should be minimized. That means from Z we should reconstruct X with the low cost. And the second constraint is about the statistical priorities. So the one that the mapping should be independent from the group. So here these two constraints allow to maintain information about X as much as possible and removing information about the sensitive attribute. And the last one is the cost for predicting the output Y. So this is the basic idea about learning fair representation. So here there is not neural network, they just use defined fairness like optimization problem, where they try to map each input to a new space by removing information about the sensitive attribute. So other methods regarding the experiment, they use three data sets. The first one, German credit, in which they have instances of bank information, and they try to predict if an instance is a good or a bad account. So here they use H as the sensitive attribute, and as well in another dataset adult incomes, where they use gender as sensitive attribute, and they try to predict if the income will be greater than 50,000 per month. And the healthcare, the heritage health price, where they try to predict if some individuals will have some hospitalization in a year, and they use the age as the sensitive attribute. So they measure their framework regarding accuracy, discrimination, and consistency. So regarding accuracy, they show that there is a loss in accuracy because they compare the algorithm with the linear regressions and regularized linear regression models that try to remove biases. And they show that they produce a better score regarding discrimination and with a low accuracy. So this is because of the information that are removed from X. So that's why the accuracy is low, but they produce a better performance regarding the discrimination. So another technique is the variational fair autoencoders, which is basically based on autoencoder, where we have an input. We try to learn a low dimension of the input and using the encoders, and we use the decoder to try to reconstruct the input. And we want to minimize the cost of the encoder and the decoder. So basically, encoder and decoder can be neural networks, and which parameters phi and theta. And so we like to input to be similar as much as possible to the input. So, and here is the cost function where we want the reconstructed input to be similar to the original input. So, this is the autoencoder framework, and another we have the variational autoencoder architecture, where we use the try to learn parameters for probability distributions and sample to obtain Z and try to reconstruct X. So here the difference is that the variational autoencoder can help to generate new input or new data. So based on this framework, they define the variational fair autoencoder to allow the latent vector Z to be free from unfair attribute. So what they do basically, they extend the variational autoencoder framework by factorizing the input data with X as non-sensitive attribute and S as sensitive attribute, and they add some regularization terms using maximum mean discrepancy to encourage the independence between S and Z. So they propose an unsupervised and semi-supervised approaches. So basically in unsupervised approaches, they split the input data of the encoder into two input where we have X, the features, and we have S is the sensitive attribute. And the rest of the work is done by the variational autoencoder framework, where they show that the latent space Z will be free from any dependence of the sensitive attribute, and in this case they obtain a fair representation of the input data. And in semi-supervised way, here they suppose that if there is a correlation between S and Y, so just by removing S without taking account the outcome or the label, they can obtain a representation that is skewed or that could not be well for the prediction of Y. So in this case, they add some regularization term, and they also integrate a new layers that use that use Y, and use the maximum mean discrepancy to enforce to enforce the distribution of the latent space Z to be similar between each group. That means the protected and unprotected group. So in this case, they obtain a Z that also return information from the predictor, and after that, the representation can be used for a prediction task or for learning a predictor model. So as a result, they evaluate the accuracy and the statistical parameters, and they show that their architecture proposed is more effective in hiding the sensitive attributes, but the accuracy of prediction of Y is also generally lower. So, and regarding this comparison, they obtain a better discrimination score than the previous method. So another technique is the flexible fair representation by disentanglement. So this framework extends the variational fair autoencoders and by different way. The first thing is that it's possible with this technique to handle or to work with multiple sensitive attributes. So here S is a binary vector representing different sensitive attributes, and they also integrate the sensitive subspace Z that are factors of variation of the sensitive attribute. So that can be hidden after to satisfy some fairness criteria. So and this technique is basically used the disentanglement, which we can define as the statistical independence between latent variables. So in literature, there is not a clear definition of what is disentanglement, but basically it's a technique that allows to find the factors of variation of the data. So here, by factors of variation, that means if we modify one factor, it didn't affect other factors. And here they suppose that there is independence between each sensitive subspace, and this is reaching sensitive subspace and with Z. So the authors was not interested in the disentanglement of the latent space Z. So this technique is said to be flexible because after the representation learning, they can based on the assumption that elements in B are independent, they can just hide some of them to satisfy some fairness criteria. For example, if we have gender and race or age, they can define to remove dependency to hide gender and age to obtain a representation that is fair or that hide the dependencies between these two sensitive variables. So this is a very interesting approach and ambitious. So here they have their loss functions where they enforce the independence between each element in the latent space B and with the latent space Z. So this is the main idea of their framework, and it's flexible. That's why they call it flexible fair representation by disentanglement. Another technique is based on adversarial learning, where they have two competing models. One is a machine learning task that try to obtain the intermediate representation, and another try to predict the sensitive attribute. So here the model the adversary will be occur when the second model will be not able to predict the sensitive attribute from the representation. So that means the information or the dependence with the sensitive attribute are removed. And the authors use a technique based on the learned fair representation. This is the first method that they presented. And here they still have three objectives in the optimization, where the first is the cost of reconstructing Z from X, and D is the dependence between Z and S, and here they obtain D by using an adversarial method for predicting S from Z, and n is the error of predicting the outcome I get from the representation. And one is interesting result is that they take a subset of pictures and they add some overlay text on them and define this picture as the sensitive attribute. And after they run their framework, they find that the effort to authenticate on establishing independence in the latent encoding with regard to EST, they find that the model practically remove the tag on the picture. So here we have one example of the image before and the image after. So here they remove the dependence with the latent space S. These latent space are pictures that contain the overlay text. So thank you for listening. I hope this was useful. There's many technical and mathematics behind that I didn't present. So I present the main idea, and this is all about the most paper on fair representation learning. So thank you.